Question 1, part 4 is asking us to trace through the first few steps of the action value function learning algorithm. They're telling us that we need to start with all Q values initially set to 0. Now, basically what this means is we're going to start with a Q table that's full of zeros. So I'm going to draw a new one down here. S1, S2, A1, A2. And start it with zeros. Now you might be wondering, like, why would you do this? We already figured out all the answers and we've made up this Q table over here with the optimal answers. Well, the thing is we've had like a really nice example in this question 1. It was easy just to inspect the world, figure out what the optimal policy was, and then work out all the values analytically. In a real world setting, this is not really realistic. Generally, we'll have an agent in an environment and it would need to learn these Q values, learn the Q value function. So the idea is that it's like an iterative process. We start down here at 0, but as we go along, as our agent moves around and learns, our final values in this Q table should converge to these ones that we did in the previous part. So this part 4 is just a little taste of sort of what that iterative process looks like. So we imagine ourselves in the same world that we've been dealing with the whole way through, except down here, our current estimates for the state and action pairs are all 0. We haven't done anything yet. We're going to start up here in the top left-hand corner of the Q value and try to estimate the Q value for this state and action pair. Well, if the agent is in state 1 and we force him to take action A1, if we remember back to our original picture, this is going to give a reward of 0 for the agent. Zero. But remember, we also have to add on the future, like a term for the future rewards. So we need a gamma in here. And the gamma is going to be multiplied with the value of the best next step for the agent. So in this situation, if we're taking A1, then we know that the agent is going to end up back in state 1. Once it's back in state 1, it looks for its best move and it chooses that. The problem is currently, actually all of the values for state 1 are all 0. So the agent really has no option but to get a 0 or estimate getting a 0 reward for anything it does. So this is the expression that tells us what we need to update this state action pair to on the first iteration. If we do the same thing, let's put this back over here. So we're done with this S1A1 pair now for the first round. Now we try and estimate what's the value for state 1A2. Again, if we remember back to our picture, this is the one that gets the -1 penalty. But if you recall, this is the one, this action allows us to transition over to state 2. So again, we're going to think about the future rewards that are coming in discounted. But we have the same problem currently with the state 2. All of our best estimates for state 2 are still 0. So the agent has no other option but to estimate a 0 reward going over there. Even though we know in the world that's actually going to be a +5 reward, at this current point of the iterative process starting from 0, the agent doesn't know that yet. So now we've looked at both actions for state 1, we start looking at state 2. So state 2, action 1 That's the one that gives us the +1 reward. That's the self loop on state 2. And plus gamma times the future rewards. Now, this loop starts on S2 and ends on S2. So, again, both of our current estimates are 0. This has to be 0. So it might seem strange, even though we know what the world looks like, the agent doesn't yet. Now, if we stop the agent here and say, all right, now you can follow your optimal policy, something kind of strange happens. Currently as it is, I'll put an actual value in for these expressions first, actually. So let's get rid of these. So 0 plus gamma 0 is 0. This one over here will turn out to be -1. And this one down here will turn out to be 1. So just stressing the point again, we know this position here, this is going to be a 5. We know that. But the agent doesn't. If we allow him to now just start acting of his own accord, we don't force him to choose A2, he's going to start choosing his optimal guess at this current point. Now, because we haven't updated this one, we haven't forced him to take A2. It's still 0. And so after he takes action 1 in state 2, he'll come back to state 2 and then assess what his best future estimated reward is. So if we look at these, he sees right here that he can get a +1 if he keeps taking A1 over and over again, as opposed to 0 over here, which he'll never take. So you can see that by not forcing the agent to check action A2 when he was in state 2, he never sees the +5 reward that's about to come up. A1 is just selected continuously over and over again. Now, I'm making a big point about this to show that this is why we need some type of randomization in our search strategy of the environment. The way I'm doing this Q table right now, I'm forcing the agent to take every single action in every single state. This allows the environment to be fully explored and allows us to see if there's like a good reward coming up like this one. Right, so just quickly fill this in. We've now got an updated Q table, A1, A2. Once we've done one round like this, we just continue and do it again. So I'll go ahead and do one more round, just to show how the numbers change on each iteration. How about we do the next one down here? So now we're going to think about estimating or updating the value for S1, A1, this one here. So if the agent's in state 1, we force it to take action A1, it's going to get a reward of 0, which is the self loop. And then it's going to be gamma times its optimal move in state 1, because obviously the self loop is going to make it end up in state 1 again. Now, funnily enough, 0 is actually the best move it can make in state 1 currently. It estimates that if it takes A2, it's going to get the -1 penalty. But if it takes the A1 again, it'll just get 0. So this remains the same. Put a 0 there. Right. Now we update the state 1, action 2 pair, the value for that. And again, we know that by taking action 2 in state 1, we incur a -1 penalty, plus gamma, plus our discount factor, times. Now, this is where it gets a bit more interesting. If we've taken action A2 from state 1, it means that we've transitioned over to S2. Now the agent looks at the S2 possibilities, and we're in a much better position than we were in the first iteration because the agent can now see the +5. Previously, when we stopped it early and that there was 0, the agent would have selected 1. But now that we've got the 5 here, it's the obvious choice for the agent. So we get 5 down here. So we finished updating the state 1 A2 pair. Now we do the S2 A1 pair. We get 1 reward, that's the self loop on state 2, plus gamma times the best it can do from state 2, which again is 5. Now that the agent can see this 5, it's always going to be taking it when it's in state 2. And then finally, when we update the state 2 A2 pair, we get the 5 reward, and then we multiply the discount factor by the best thing that we can do in state 1. Now, it looks like here that the best thing that we can do is actually still this 0 here. But remember, we've actually, in this round, we've been going through updating them. So it'll be the discount factor times this quantity here, which would be 4.5 minus 1. So this will be 3.5 here. So now I'm just going to go through and change these expressions to numbers. So this one will still be 0. Put a 0 there. This one will be 3.5. This one will be 5.5. And this one will be something I can't do in my head. So let's go 0.9 times 3.5. That's 3.15 plus 5 is 8.15. And obviously we need our headings for our table, S1, S2, A1 and A2. So you can see how round by round, these numbers are changing. And if we do this enough times, this table, the values in here, will converge to the actual optimal ones that we calculated analytically. So that was part 4 for question 1. We traced through the first few steps of the action value function learning algorithm. That's what we did here. We did 2 steps of that algorithm, beginning with our Q values at 0. And we also talked a little bit about why it's necessary to force exploration. In this situation, we stopped the agent early before it had seen the +5 reward, and talked a little bit about how it would constantly be selecting a suboptimal move if it wasn't forced to explore that extra step.